Hey everyone, welcome to TitanClass. Cue the intro. On this episode of TitanClass, we're going to be talking about a ton of pre-calculus stuff. As a matter of fact, 5 different topics. First topic will be special right triangles. I'd like to focus more on the 30, 60, 90 right triangles. I have a few 45, 45, 90, but they're a little bit easier to solve, as we'll work alongside each other today. Part 2, coterminal and reference angles. Part 3, radian to degree conversion rates and backwards. DMS conversions and backwards. And a little circular motion. So let's get started. Oh, by the way, did I mention that I have 50 problems that I'm going to solve for you? I know you were probably wondering what TitanClass was. Well, TitanClass is a way for me to do problems over and over again, so you can kind of get the idea of the thought process and how to solve them. So sit back, relax, and enjoy the show. Part 1, special right triangles. I'm going to do the problems on the board here for you. I'll leave some of the answers on the side so you can reference back to them if you need to. Again, we got 50 problems of a mixture of these things. Let's start. Problem 1, special right triangle. Do my best to draw it. That's not a good right triangle. That's okay. So this is going to be a 60, 30. I've got 3 root 3 on the bottom, and I'm trying to find y and x. Okay. First thing that we want to remember is, what are the rates? What are the ratios of these special right triangles? Well, a 30, 60, 90 is going to give us 2x for the hypotenuse, and I want to write this somewhere where we're going to keep it. So let's say we have 2x is always going to be the hypotenuse. X is always going to represent the short side, and x root 3 is going to represent our long side. Right? So if you remember these 3 concepts or these 3 pieces, you should be okay to solve the rest of the right triangle. So what are we given here? I know that 3 root 3 is going to represent my short side of x. Well, if I have 3 root 3 for the short side, let's go to things that we can solve quickly. I have to multiply the short side by 2 to get to the hypotenuse. So all I have to do is multiply this value by 2 to get to x. So x is going to represent 6 root 3. Because if I multiply by 2, I don't actually do anything to the root 3. I'm just multiplying the 3 outside, or the coefficient of this radical, by 2 to get 6 root 3. Now, if I want to find out what y is, I'm just going to plug in what I know is x to that x. But it's going to be a little bit messy. So this y is going to be 3 root 3 times root 3. Because remember, it was x root 3. So what I'm doing is I replace this x with 3 root 3. Now, I have to multiply these two things together, obviously, to simplify. So 3 root 3 times, that's a 1 root 3, is going to give me 3 root 9. But we know what root 9 is, it's 3. So this is going to be 3 times 3, which is 9. So my answers for number 1 is x equals 6 root 3 and y equals 9. Moving on. Only 49 more to go. Now you might be saying to yourself, do I have to watch this whole thing? Yes. I erased the thing I didn't want to erase. No, you don't have to watch the whole thing, obviously. I don't know why you wouldn't want to, but we'll get there. Try to remind me not to erase this next time so I don't have to keep doing this. I'll put a box around it. That'll make it permanent, right? Maybe not. Okay, number 2. Same type of right triangle. That's a way better one. Thank you. I know. It's like a computer did it. 60 degrees is given. 2 is the short side. Again, we have a y and an x. Okay, this might be a little bit easier because I have an integer value, right, that I can just manipulate. So again, short side is 2. My key here says that I multiply 2 times that short value to get my hypotenuse. So that means x is going to be 4. Now, this is actually super easy Because if this side, the longer side of the two legs, is x root 3, and that's x, I'm just plugging in what I know. So my long side is going to be 2 root 3, and I have my answers for number 2. Super easy one. X is going to be 4, and y is going to be 2 root 3. All right? Let's move on. I'm actually not going to erase this triangle because the next problem looks just like it. See, I'm evolving. I'm getting smarter through the process. All right, number 3. This is root 3. This is y, and this is x. Okay, now here's what we need to do. Short side is root 3. I multiply the short side by 2 to get to the long side. So if I multiply this by 2, then x is just going to be 2 root 3 because there was a 1 in front, right? So I just multiply that by 2. Now, y we know is x root 3. Well, I'm just replacing or substituting root 3 into that x. So this is going to say root 3 times root 3. Kind of similar to the first problem that we did. Well, root 3 times root 3 is root 9, which is just 3. So my y value is 3, and my x value is 2 root 3. Okay. Let's go for number 4. And number 4 is going to be our beginning of, I think, some more difficult things. Okay. You can't see that. All right, number 4. Here, we have x as the hypotenuse and y is the short side, and 2 root 3 is going to be my long side. Now, on first glance, this looked really challenging. Obviously, it's not going to be that challenging, and here's why. The value of the long side is x root 3. So because the root 3's are the same, x is just going to be my value of 2, or my missing short side value is just whatever this coefficient is of this radical expression. So y is going to be 2 here, which means I multiply that value by 2 to get my hypotenuse. So this is going to be 4. Right? So that was actually way easier than we had thought, where x is 4 and y is 2. Again, hypotenuse, short side. Okay? Number 5. Okay. Number 5. Now, it actually doesn't give me the 60 here, but we're not going to change the triangle because these are all 30, 60, 90s that we're working with to start. It gives you 30, which obviously knows that this is going to be 60 here and 90. So let's see what we've got. It's labeling this is x, this is y, and this is 2 root 3. Okay, this is going to be a little challenging. Here's what we know. The hypotenuse of this right triangle is 2 root 3. That is its measurement. But based on our key, we also know that the hypotenuse is 2x. It is 2 root 3, and it is 2x. Well, because it's both of those things, that means we can set up an equation where 2 root 3 will equal 2x. And why can we do that? Well, because if they both equal the same actual side, they're both hypotenuse, I can set them equal to each other. And we have to do that because we want to solve for x. We don't know what the missing value is really. So let's go ahead and do that. So 2 root 3 is going to equal 2x. Divide by 2 on both sides, and that's going to cancel out those 2's. Root 3 is going to be the x value. Now again, why did we do that? Well, I know that the short side here, based on my key, is whatever x represents. In this problem, it just says it's y. It could be any letter, it doesn't matter. But if I can find one of these 3 values, the object of this entire thing is we can use our key here to find the other one without having to use actual SOHCAHTOA or right triangle trig. So 2 root 3 here, that means the short side is root 3. Now again, I'm going to substitute that root 3 in for my long side because my long side here is x root 3. That's x. So now I'm just going to combine these terms and simplify previous to the other problem, and that's going to be 3. So I've got my values here, 2 root 3, and 3. So x was, I just wanted to make sure that I don't switch those things around. And y was the root 3, which was the short side. All right, let's move along. Okay, now the next couple problems, it looks like these triangles have switched around a little bit. So let's change that up. All right, so number 6, our triangle looks kind of like that. And this is the right angle box. 60 degrees, n 8 root 3 m. Okay, still a 30, 60, 90. It's on its side a little bit. I apologize again for the drawing. I was never really a good art person. So here we go. 60 degrees, 30 degrees. The side that has the 30 is always x root 3. The opposite side of the 30 is always x, and we know that m is always the hypotenuse, or 2x. All right, so let's start with what we have. Because the root 3 and the root 3 are the same here, the 8 is going to be the thing we can pull out, which will be the short side measurement. So x is going to be 8 here. And then our hypotenuse is 2 times x, or 2 times 8, which is going to be 16. So in this one, we don't have an x and a y, we have an m and an n. So for number 6, we have m is going to equal 16, and we have n is going to equal 8. Okay. Number 7. Okay, we'll go back to our right triangle here. It's giving me the 30 measurement. It's giving me a short side of 5 root 5 over 2, and then we're looking for A and B. Okay, so we know the short side, which is x, is 5 root 5 over 2. All right, now, what can we do here? Well, if I know that the short side, all we do is multiply this by 2 to get to the hypotenuse, we can actually go ahead and do that, right? So when I multiply this entire value by 2, all I'm really doing is distributing that 2 to the numerator. But because there's a radical portion of this, we don't distribute the 2 to both things. This is actually kind of one term here, right? So we're just going to multiply that 2 times that 5. Because really, when we multiply by any integer, I'm really multiplying by a fraction. So 2 over 1. The 2 just multiplies to the 5. Now what is that going to give us? That's going to give us, I don't want to mess this up. It's going to give us 10 root 5 over 2. Now, yeah, that is the value of the hypotenuse, but there's a problem here because I can simplify the fraction part. 10 over 2 is going to be 5, right? So this is going to simplify to 5 root 5. And that is going to be the length of my hypotenuse, 5 root 5, okay? Now, let's go to the x root 3 part. So if this is x, right, because that's the short side, and this is x times root 3, we're going to have to manipulate this a little bit. So we knew that the long side of a triangle, 30, 60, 90, is x root 3. Well, the x part I can substitute, right, because that's 5 root 5 over 2. I'm going to multiply that times root 3. Kind of the same process of multiplication as we did in the previous problem. All I'm really doing is I'm multiplying this fraction, root 3 times 5 root 5. Now, I do want to combine the correct terms, the like terms. I'm not actually multiplying that outside coefficient 5 by root 3. I'm multiplying the radical parts together. So what is this going to give us? That's a 2, by the way. I apologize. This is going to be 5 root 15 over 2. Because I'm multiplying the 5 radical and the 3 radicand together to get the 15. I can't simplify the fraction, nor can I simplify the root 15 because the square root of 15 is irrational. It doesn't have a perfect square factor. This is actually the answer for the long side. So we've got a mess here, so let's try to clean it up a little bit. So A was our hypotenuse, and that is 5 root 5. B was our long leg, or our long side, and that is going to be 5 root 15 over 2. All right? That was a tricky one. Let's keep it moving. So the key is, obviously, again, we don't want to use right triangle trigonometry in terms of SOHCAHTOA to solve for these things. Because doing that is going to make a big, big mess and stuff that we don't actually need to do. It's going to make you do more work, actually, over time. So we're trying to expedite and make a more efficient process. Number 8. Okay, 60 x 3 root 3 and y. Okay, we can fill in what we know. We know that's 30. All right, so the x root 3 side needs to be adjacent to the 30-degree angle. So this is supposed to be x root 3 according to our key below. Well, because again, the root 3 and the root 3 are the same, all I need to do is kind of pull out that x part, which is 3, which will be our short side. So y is going to be 3 here. And then x, which we just know is 2 times the shorter side, is going to be 6. Right? So 8. We've got an x value of 6 and a y value of 3. I know what you're saying to yourself. When do they get harder? Hopefully soon. Because if not, I'll interject some crazy things. Number 9. Oh, I probably shouldn't have erased that last one. 60. V, U, and 3. Okay. So again, we can plug in things that we know to make it a little bit simpler or to be a little bit more familiar with the process. The hypotenuse is 3. All right, so this is going to be a little bit more challenging. Good. The hypotenuse is 3, and the hypotenuse is 2x. Well, we're trying to boil this down to find x. Take a look at the key, right? What do all 3 of these things have in common that we can identify very easily with? And the answer is x. They all have an x in common. So if we can boil down something that isn't really ready for us to boil down to x, then we're good to go. We can actually apply that rule to everything else. So let's try to find out what x is going to be. The hypotenuse is 3, and it is 2x. So let's solve that. If I divide by 2 on both sides, I clearly have my answer for x, where x is going to be 3 over 2. All right. Well, if x is 3 over 2, I know the short side measurement, 3 over 2. Now, I know what the long side measurement or the long leg measurement is, and that's x root 3. Well, remember, that's x. So let's just kind of put things together. We have 3 root 2 times the square root of 3. Well, again, I'm just putting that root 3 in the numerator because that's how we multiply fractions. So my long side answer is going to be 3 root 3 over 2. And we have 3 over 2 for v. Right? So I want to make sure how they put it here. They put u first. Okay. So u is going to be 3 root 3 over 2. And v is going to be 3 over 2. Now, I know the question may come up too, where why aren't we using decimals? No, we're not using decimals. That's not good. When we talk about trigonometry, when we talk about pre-calculus, decimals are not always super preferred. We try to avoid them as much as possible because decimals are not exact. They are rounded. Everything that you see up here, though, is exact. Now, I know that may not make any sense because, like, the square root of 15, how is that exact? It actually is very exact. When we talk about radical signs, when we leave radicals, radicands, the reason we do that is because otherwise they would be decimals. And without additional information or additional direction, we wouldn't know where to round them, right? So we leave it as the radical because that's exact, right? Let's take a look at number 10. And what I'll do is after I put 10 up here, I'll erase these and then we'll go to the next ones. Number 10, 60 degrees, m, n, 2 root 3 over 3. Okay, 30 degrees we know. All right, now, short side. The short side is always opposite of the 30 degrees, and x root 3 is always adjacent to the 30 degrees. Okay, so if this represents x, and I know the long side is x root 3, we can substitute this x into the x for here and simplify. So we have 2 root 3 over 3 times root 3. I'm going to combine the terms of my multiplication, so I'm actually just going to be multiplying the root 3 times the root 3. This is going to give us 2 root 9 over 3, or 2 times 3 over 3, which is 6 over 3, which is just 2 because the 3's cancel. So the long leg measurement is just 2. Now, the hypotenuse, let's go back to x here, right? If x, all I need to do is multiply that by 2 to get the hypotenuse, all I need to do is multiply this 2 by 2. So it'll be 4 root 3 over 3. Nothing can be simplified here because 4 over 3 is a very nice improper fraction. So we have our values here. So number 10 for m is 4 root 3 over 3. And n was 2. All right. So You can take a picture of those and then go through the process again and see where we went if you wanted to practice them on your own. I'm going to go ahead and erase these, and then we'll go back and we'll try number 11. And that will be the start of our 45, 45, 90s. And you're probably thinking to yourself, how come you didn't edit through this? I don't want to. I did not want to. I am going to erase it this time because a lot of ours are 45, 45, 90 now. Oh. Titan is making his daily appearance in the videos. Thank you, sir. Number 11. All right, now. Okay, this doesn't look like a 45, 45, 90. I promise you it is, because I'm labeling it as such. Okay, so in a 45, 45, 90, let me put a key after I put this down here. So the key for 45, 45, 90 is both legs are x, and the hypotenuse is x root 2. Very squeaky, I apologize. Okay, so both legs will always be the same value, the same measurement, and the hypotenuse is always x root 2. Now, why are both legs the same measurement? Well, in geometry, there's this thing called symmetry, right? So if both angles are the same exact measurement, that means they open up and they have to have the same distance of their adjacent legs. So these two values, this side and this side, will always be the same measurement. And this is always going to be whatever that value is, root 2. So if we have a 10 here for the leg, that means y also has to be 10. And x is going to be 10 root 2. So that's pretty simple. 45, 45, 90s are a little bit simpler than everything else, right? So we'll do this. We'll say x is 10 root 2 and y is 10. All right? All right, these actually twist and turn all over the place. Number 12. All right, so that's a right angle box. I'm sorry. 45, y, 4 root 2, and x. Okay. The right angle corner part is kind of like an arrow. It always points to the hypotenuse, right? That's kind of the way to remember it. So if x is the hypotenuse, let's just chill for a second. This measurement and this measurement need to be the same. So y is going to be 4 root 2. Okay. Now, remember that that's x. That's the value of the leg. The hypotenuse is x root 2. Okay. So if this is the leg and the hypotenuse is x root 2, I'm going to substitute what I know for the leg, x, into that x. So I'm going to have 4 root 2 times root 2. Because this is what the radical means. It means x times root 2. We just don't put the multiplication sign there because it's irrelevant. So now I'm just going to multiply these out, right? So this is going to be 4 root 4, which is 4 times 2, which is 8. So the hypotenuse of this right triangle is going to be 8. So for number 12, we've got x equals 8 and y equals 4 root 2. Right? Okay, number 12. Number 13. Oh, we're flying through these, huh? That's good. That's really good. All right, 13. Okay. Kind of an upright right triangle, 45. X, y, 9. Should be relatively simple, right? This is a leg. This leg has to be the same. That's going to be 9. And I'm just going to substitute the 9 in for the x part, so this is going to be 9 root 2. All right, so very, very simple problem. Number 13, my x value is going to be 9 root 2, and my y value is going to be 9, right? 45, 45, 90s are real slick, right? They're pretty simple compared to your 30, 60, 90s. 14. Okay. U, V, and 2. Okay. A little more of a challenge, right? So I'm only given the hypotenuse, and that's 2. Now remember, I can't just substitute the 2 into these values, because although these are the same, the measurement of the hypotenuse, remember, is x root 2. So let's go back to the same theory, the same concept that we've been using before. The hypotenuse is 2, and the hypotenuse is x root 2. So we want to use both of those, equal them together to solve for x, because then I can find x, because we have our key here that helps us. So the hypotenuse is 2, and the hypotenuse is x root 2. Not bad. So let's solve for x by dividing by root 2 on both sides. Now, we cannot leave the fraction like this. And one of the biggest rules of operations with radicals is we can never leave a radical in the denominator. This is not simplified. This is wrong. This is not a good value for us. So we're going to do something called rationalize the denominator. What that actually means is we're making an irrational denominator rational because we are rationalizing it. The way to do that is we create a new fraction with root 2 over root 2. Whatever the denominator is, radical part, we make a fraction root 2 over root 2. Then we multiply across. Top is going to be 2 root 2. We get real simple for each other. We can just do root 4 here and then go to 2. But anytime we have a radical times itself, meaning a radical times a radical, it's just the number underneath. Now, again, we're not actually there yet because I can simplify this part. The 2 over 2 cancel. Root 2 is my answer, which means that both v and u are root 2. It's funny, I don't know if you can hear him barking. He's really far away from us right now. He's like downstairs in like another room, and he's barking. And I don't know why. Hey, we got a marathon going here, brother. I can't be coming downstairs. What? I tell you, his breed talks back like you wouldn't believe. Like you wouldn't believe. There's 2 more in this section, and I'll move on to part 2. Number 15, 8 root 2, x and y. Okay. Hypotenuse is 8 root 2, but we got lucky because there's a root 2 built into our memorization of how the hypotenuse is. So really and truly, what is my x and y? And they're both 8, right? Pretty simple one. So both x and y are 8. Okay. Last one in the sequence, and then we'll move to something else. 16. Right angle box. That's not bad. 45 x, y, 3 root 2. You know what? We're getting too lucky here. Let's make this a little bit more challenging, huh? Let's do this. Let's say that was the problem. Let's make it a little harder. Let's say that this is 6 root 5. Let's make it a little more challenging. All right, so we know the hypotenuse is 6 root 5. Cool. Well, that's not a root 2. If that was a root 2, I could just say that it was 6. That was actually what the problem was going to be. It was going to be 3 root 2, but that's too simple. Remember what we do when we don't have radicands that are nicely translated. I know you probably heard that. He's crazy. Okay, the hypotenuse is 6 root 5. And the hypotenuse is x root 2. Hypotenuse equals hypotenuse. That makes sense. Let's solve for x so we can find out what the other 2 legs are. We're going to divide by root 2 on both sides here. Canceling out the root 2's. Just like a previous problem though, I can't leave a root 2 in the denominator. I can't leave a root in the denominator. So what we're going to do is we are going to rationalize the denominator by creating a new fraction. And you did this in Algebra 1, hopefully. And we'll multiply across. So this is going to be 6, and the root 5 and root 2 can multiply to get root 10. So we're going to have 6 root 10 over 2. Not quite there yet. I can simplify the fraction 6 over 2, which is going to give us 3 root 10. And that represents both my x and y measurement. So x and y in this particular case is 3. My x and y is going to be 3 root 10. And root 10 can't be simplified because it's irrational. All right, not bad. Looking good. All right, let's move to something else. I'm going to keep those up there until we get to the next 10. It's a nice way to remember where we are. Coterminal and reference angles. Let's go. Coterminal. This is going to be number 17. All right. I've got a coterminal angle, or I've got an angle that's 1,005 degrees. I need to find a coterminal angle that's between 0. I actually could do theta here. I'll do theta on the next one. So here's what I'm looking for. I'm giving you an angle measurement that's 1,005 degrees. The set of problems that we're going to be working with now, 5 of them, is I want to know which coterminal angle will fall between 0 and 360. So this is far bigger than 360. So what we're going to do is, we know that one revolution is 360 degrees. We're simply going to be subtracting until we get to a value that falls in between here, right? So let's do that. So I know I could just subtract 360, but I know the answer to that isn't going to get us anywhere near there. So actually, let's do that twice. Let's subtract 360 2 times. So again, the reason we're doing that is because one full revolution is 360 degrees. I'm really trying to get down to like the base part of this before I have to repeat the circle again. So if I subtract the rate of 360, I will eventually get to something between 0 and 360. So I'm going to do 1005 minus 720, right? And that's going to give us that value there. And I'm going to get 285. That is a coterminal angle to 1005. So my answer here for number 17 is going to be 285 degrees. Now again, what are we talking about? 1005, it starts out in our initial position, or our starting value here, right? Here's what we start out with. So 1005 is going to be multiple rotations around our unit circle, multiple rotations around the coordinate plane. Now, what's the base value of this? If I were to just get rid of the extra rotations, 285 is going to be the measurement. Yeah. Maybe the Amazon guy, I don't know, because he's really barking. I don't know if you could hear that though, because he's far. So 285 is our base value here. Well, 90 from here, 90, 180, 270, it's probably here, right? So this angle is 285 degrees. Remember, this is the terminal side. Initial side, terminal side. It opens up like this, right? So I'm finding a coterminal angle to this. Yeah, I certainly could have done that value, but I want something between 0 and 360, meaning negatives don't work. This way is negative. So I really need to just find multiple endpoints after a couple more revolutions. As long as after those revolutions I end on that line, it doesn't matter what way it went, because I could have went positive and kept positive and positive, which this was, or I could have went negative. But because the stipulation was I needed it to be a positive value, 0 and 360, we have to go with the positive result. The next couple in this set are going to be like that as well. Let's try some more. These should go a little bit quicker because there's not really too much calculation to do. Number 18. Number 18 is 795 degrees. Again, I'm looking for something that's between 0 and 360 degrees. And I'm going to use theta here because we really should use theta when we talk about these measurements. The angle measurement is 795, which means there was multiple rotations around the coordinate plane here. So let's boil this down until we get to something between 0 and 360. If I subtract 360 from this, it's not enough, right? I'm going to get 435. Seems like a pretty easy calculation. So we're going to have to do that again. One revolution we're taking away, a second revolution we're taking away. It's like basically a rerun. It did it twice. We don't want twice. We want it to its base one time around, or just before it got to one full time around, right? Didn't move at all at 0 degrees. It moved to its starting point again at 360. I can't have it at either of those points. I need it where it was in between. So let's do that a couple of times, and our value is going to be 75 degrees. So a coterminal angle to 795 that falls between 0 and 360 is going to be 75. All right, I'm going to keep that there. Thanks for reminding me. 19. Okay, negative 600. All right. Tricky, because our question, the initial value here, the initial point here is negative 600, negative. So I'm going to have to add 360 to this multiple times because I need my answer to be positive. Remember, I need it to be in the positive range from 0 to 360. So let's say we added 360 to this one time. I'm still not going to be in the positives. Let's add 360 again. That will get me positive. It's going to be so positive, in fact, it's going to be 120 degrees. So a coterminal angle to negative 600 degrees is 120 degrees. Now again, think about this for a second. I've got a 600 here and a 120. When I add them together, regardless of the sign, I'm going to get a value that is divisible by 360. because 720 is divisible by 360 because it happens twice. Case in point, the two 360s, right? So 19 is 120 degrees. Let's go to number 20. Negative 65. Okay, this one's probably pretty easy. I am not outside of the boundary of one rotation or one revolution. I'm still within one revolution. Now I can actually draw this one to make it a little bit easier because there's not multiple revolutions here, right? So remember, negative angles are going to be from my initial value, and it's my initial starting point, and they're going to go clockwise here, right? So negative 65, let's say this is 45, let's go here, right? So this is the negative 65 degrees. This is the terminal point. This is the terminal end here. So to find out where I'm going, remember that we're negative, so I can't keep going, right? I need to go the other way. So if I go the other way, meaning the distance from here, I'm going this way here. So the difference between those two things is just the addition of 360 to it. Because remember, it's coterminal angle and its other pair of coterminalness, that probably doesn't work, is going to have to be addition to 360. So this is going to give me 295. Because this angle is 295 degrees. Because the 295 and the 65, regardless of the sign, will equal one full revolution of 360. So number 20 is 295 degrees. All right. All right, let's move on. Let's go on to another set. And this next set is going to be if the given angles are coterminal to each other. So it's going to give us two angles, and we have to decide whether they are coterminal or not. And this is going to be 21. All right. Two angle measurements. I've got a 35 degrees and a 755 degrees. Okay, a couple of ways we can do this. We can do the algebra way, or we can do just the eyeball way. Well, let's think about this. They're both positive values, so theoretically, I should just be able to add one full revolution to 35 a couple of times, and if I get 755, I'm good. So let's try that way first. So if I added 360 to 35, I'm certainly nowhere near 755, but it gets me closer. That's 395. If we add 360 again, guess what? I am going to get 755. Because that revolution, all I had to do is add two whole ones, and I get to what I'm looking for, they are coterminal. So the answer to 21 is they are coterminal. The algebraic way to doing this is a little bit more in depth, but it's a little bit more obviously algebraic. We take the first value, 35. We know that if we added 360 degrees, which is one full revolution, times a value that represents the number of revolutions, I should be able to equal to the other angle measurement. Now, again, do you have to do this all the time? No, absolutely not. For ones that look a little funky, I probably would. So again, I take the first value in sequence of 35 degrees. I'm going to add that to the quantity of one revolution's worth of degrees times how many revolutions. K in here represents the number of revolutions. And obviously that can be positive or negative, which is fine. We're trying to solve for K. So let's actually do that here. We already know they're going to be coterminal, but let's see what's happening. I'm going to subtract 35 on both sides first. Again, pure algebra all the way, solving an equation. This is going to give me 720. You see where I'm going already. 720 degrees is going to be 360 times K. Well, when I divide by 360, isolating the K, I get a value that is an integer. Because my value is an integer, whether it's positive or negative is irrelevant, I know that they must be coterminal. Now, if this value was a decimal, they would not be coterminal because there isn't the same ratio or scale factor or slope, if you will, of 360. They have to be multiples of 360 degrees to be coterminal. If they are not, then they're not going to be coterminal. And we'll do some in a minute that are probably not going to be coterminal. But for this particular one, it is. And I can leave that equation up here, and we'll just do a little craziness here. So let's do SV, which is starting value of the degree measurement, plus 360K, and that's going to equal terminal value, right? Nice. I just made that up. I don't know if that's actually a thing or not. It should be. 22. 100 degrees and negative 440 degrees. Okay. Well, we know that we're going to go from 100 degrees and we have to go negative. So I'm going to be subtracting 360 a bunch of times to see if we can get there. So let's subtract 360 first. That's going to give me negative 260. Certainly not the negative 440. So we'd have to do another revolution. Let's do a negative 360 again. And it's not going to make negative 440. It's going to go far less than negative 440. We're going to get like a negative 620 here, right? So no, they are not coterminal. Now, I'm only going to do this one more time so you can see the process that will not work. Let's use our handy formula here to help us. Terminal value is negative 440. Starting value is 100. And we're going to add that to the quantity of 360 times k. We'll subtract 100 on both sides. Again, degrees. That gives us negative 540. And that's going to equal 360k. When I divide by 360k on both sides, not k, sorry, I'm going to get a value here that is not an integer. So I'm going to do some crazy stuff. K is not going to equal the set of z. Z stands for the set of all integers that are known to humanity, which is an infinite amount of integers. I just say the set of z, so it makes it a little easier so you know that it's not a whole number. Okay, high level stuff right there. So number 22, they are not coterminal. All right, 23. 290 and 650. You're going to get so good at these things that you're not even going to have to add or subtract on paper. I know I'm going from a positive value to another positive value, so I'm going to have to add one more full positive revolution. So let's add one more full positive revolution, and I will get 650. 23, they are coterminal. Okay? Meaning they have the same terminal endpoint, the same terminal end. 24, 270, and 630. All right, well, let's find out. Again, I'm going to be adding another full positive revolution. So when I do that, guess what? I get 630. Exactly what we're looking for. 24 is also yes. Okay. Last one in the set. We've got a 65 and a 165. We don't even really need to do anything here, right? Because there's only 100 degrees in between. These are clearly not coterminal. So 25 is a no. All right, not bad. All right, next set of problems. We're still going to be in the coterminal range of questions. This set, though, is going to give us a value. So this is 26. The value is 370 degrees. In this set of problems, we're looking for one positive and one negative coterminal angle. All right, so here's what we're going to need to do. 370 degrees is already positive, but we can't use that because that's cheating. I need another, or the next positive coterminal angle. I also need to get a negative one. So really what we're trying to do is we're going to be adding 360 and subtracting 360 from this value independently to try to find our values. So let's do this. I could certainly add 360 to get to the next positive coterminal angle. Do I have to, though? And the answer to that is not really. Since this is already more than 360, I can subtract one full revolution and still get a positive result. Now, is your answer going to be wrong if you add 360 to this? No, not at all. But it just might be easier to find the subtraction of it because it's more than 360. So let's try this. If I subtracted 360 from this one full revolution, I get 10. Well, 10's a positive value. We're going to use that as our positive coterminal angle. Now, we're in the same mindset. I'm going to need to subtract 360 from this value to get my first negative coterminal value. So if I subtract 360 from that, I'm going to get negative 350, which is the negative coterminal value in termination or in relationship to 370. Right? So we've got two values here. For number 26, my positive one is 10 degrees, and my negative one is negative 350 degrees. Right? Not bad. This set of problems is going to be all like this. Number 27. Negative 150. Okay. This particular one, I'm going to have to definitely add and subtract on both sides. So let's just go ahead and add it because we know that 360 is more than 150. So if I add 360 to this, I will get my positive result, which is going to give me a 210-degree angle. Now, negative 150 is already negative, so we can't put that because that's not coterminal to itself. I have to add another negative revolution. So we'll subtract 360 from that, and we'll get negative 510. So we have our positive coterminal and our negative coterminal. So we've got a 210 and a negative 510. Looking good. 28 already? We're flying, huh? I don't even know what time it is. You do. If you've been watching the whole thing, you're serious business. All right. Number 28. 420 degrees. I'm going to be adding and subtracting some things here, but I don't really have to add, I guess, because it's more than 360. So I can subtract both times, just like one of our first problems, because this is far greater than 360. If I subtract 360 from this, I'm still going to be in positive range. So 60 degrees is going to be my positive coterminal angle. Now I'll subtract 360 again from this, because I need to go to negatives, because again, I need a negative, and I'm going to get negative 300 degrees. Okay? I think there's two more in the set. 29. 334. All right. This value is just a little under 360, so I am going to be adding for one side and subtracting for the other. So let's add first 1 full revolution's worth. That's going to give me 694 degrees, which is my positive coterminal value. And then let's go back and subtract 360, which is going to give me 26 degrees negative. That's my negative coterminal. Okay. Last one in the set, and then we'll move on. Number 30. Is negative 30 degrees, okay? Just at the 0 range about, so we're gonna add and subtract, right? So let's add 360 for 1 full revolution, which is gonna give me 330. That is the positive coterminal angle. And then let's go back and subtract 360, which gives me negative 390. And that is my negative coterminal angle. All right, looking good, not bad. Let's move it along. All right, next set, reference angles. So the next 5 problems are going to be reference angles for us. We're on 31. Remember what a reference angle is. A reference angle is always got to be 2 things. It's always got to be acute, and it's always got to be positive. So our first problem is 140 degrees. Find a reference angle to 140. Okay, well, we always know that we can draw these things to help us out a little bit more. So here's my coordinate plane. 140 is a positive value, so 90 and another 50, maybe about here or so. So 140 is this measurement here, right? A reference angle has always got to be positive and it's always got to be acute. Our reference for the reference angle is the x-axis. That's what we're looking for. So I'm looking for the difference between the terminal point of this 140 and the x-axis. Well, we know that our x-axis, a straight line, is going to be 180 degrees. So my reference angle for 140 degrees is the difference between 180 and 140. So 31 is 40 degrees. 32. 165. Okay, well, kind of similar to the last problem. I know that 165 is a positive angle. I'm looking for the difference between 165's terminal end and the x-axis. So that little sliver, right? So 180 minus 165 is 15. Not bad. That was too easy. 33. Negative 84 degrees. Huh. Uh-oh. Negative 84. Well, negative 84 is already acute. Negative 84 is a negative angle, so I'm going to be going clockwise. And if this is 90, it's going to be about there, right? That's negative 84. It's not often you see these types of problems, but if you do, don't fret. It's not going to change the language or the definition of a reference angle. Reference angles need to be two things, positive and acute. I can't go the long way here to the x-axis. I have to go back the short way. So in this particular case, the reference angle to negative 84 is going to be 84 degrees. And again, this doesn't happen very often because there's not much reason to do a negative acute angle already. But in the event you do see that, which you may, just make sure you go back from where you came from. It's going to be the positive value of that same number. Oh, where was I? Oh, 374. Okay, so 374 had a revolution already in it. So if we have a revolution, we can make this a little bit easier and take away one of those revolutions to see where that angle would have landed. Because remember, adding or subtracting 360 degrees to numbers just makes that angle the same exact end or terminal point. It just made it one more rotation around, right? So let's take a look and see what we got here. 374, if I started my initial value, is one full way around, which is 360, and then 14 more degrees here. So this is going to be a really, really small looking angle, sort of, but that was the after part, right? So it ended up actually going here. It started at the initial point and then went around. I probably did that wrong, but you get the idea how there's an overlap. So this is going to be my 374 degree angle. So because we could have subtracted 360, the one revolution from that, really what we're looking at is a 14 degree angle. The 14 degree overlap from one full pizza pie to that little section. Well, if I want the reference angle to 374, I'm just going to get rid of that 360, that meaningless, regardless, I don't need anything, and get to 14. Well, because 14 is positive and because it's acute, 14 is my reference angle. Titan's really upset at something. I don't know what. Maybe because I'm up here again. All right, last one for reference angles. Negative 96 degrees. Okay, let's draw it. If drawing it helps you out, please go ahead and do it. So a negative means it's going to be a negative angle, which is clockwise, which is the direction of my hand. 90 from this point to here is 90. So another 6 is about here or so. So this probably is a negative 96 degree angle. All right, well, this is not too bad because, again, I'm trying to find the difference between the x-axis and this value, the x-axis and this terminal point. Well, I can just take the 96, again, irregardless of the sign, and subtract it and find the difference, right? So what I'm really doing is I'm finding 180 minus 96, which is 84. Two 84s? It's weird. Okay, because again, if negative 96 is this measurement, I'm looking for this distance. Right, I'm looking for the x-axis to that terminal point. All right, let's move it along. Only got 15 problems left, everybody. Hope you're having fun. I know I am. All right, next set of problems, radian to degree conversion rates. Okay, some basic rules. Radians to degrees. You will take whatever the radian you are given, and you are going to multiply that by 180 over pi, and you will get a degree measurement. The reason that we multiply by 180 over pi is because radians will have pi in the numerator. I need a numerator denominator pi to cancel out, because that's what I'm trying to do. I'm trying to get rid of pi when I'm trying to move to degrees. And again, we're doing it by 180 because that is 1/2 of the revolution around, which is the relationship of 180 degrees, pi radians. 180 degrees is pi radians, right? So we're just using that ratio to help us convert. And then degrees, if I give you a degree measurement, you would enter it here, and we would multiply that by pi over 180, and that gives me the radian, right? These are super, super important. The way we can remember this is, if you have a radian, you've got pi in the numerator somewhere. Pi's got to be in the denominator to get rid of it. if we have a degree, we're trying to introduce pi into that problem or into that measurement. So pi needs to be in the numerator. When things are in the denominator, they go away easily. When things are in the numerator, they don't go away easily, right? So that might be a little bit easier to help solve these things. All right, so number one on this, number 36, is pi over 3. So the first thing we want to do is identify what we're given. Again, I've got pi. That's a radian measurement. So I'm trying to convert it to degrees, so let's do that. So this is going to be pi over 3 times 180 over pi. And again, I'm using the top conversion rate because I need the pi's to be on top and bottom so they cancel. They will if I do cross cancellation. And then I have 180 divided by 3, which is 60. So pi over 3 radians equates to 60 degrees. Some of you are already good at this. You can obviously skip this section. You don't have to watch this section unless you just want to. Number 2, 7 pi over 3. I've got pi. I know I have radians. I'm trying to convert to degrees. So let's do that. We're going to do 7 pi over 3 times 180 over pi. All right. The pi's cancel. 180 over 3 is 60, and 60 is in the numerator, right? Because 180 is big, or than 3. So this is going to be 7 times 60. Well, 7 times 60 is 420. So 37 is 420 degrees. Now, we're going to get good at this process where we say to ourselves, ooh, well, we know that 420 degrees or 500 degrees or 800 degrees is multiple revolutions. That can happen in radians as well. Think about what I had said earlier. 180 degrees, half of a circle, is pi radians. Well, if I have 7 pi over 3, that means I made a couple of rotations, at least one full revolution around the circle. And again, we're going to get to that point where you're going to be really good at identifying those things. 38, 290 degrees. Pretty simple. We did some radians before. No pi here. We want pi to be introduced. So we're going to do 290 times pi over 180. Simplifying this is going to get a little messy, right? Because this is now going to be what? 290 pi over 180. What do they have in common? I can divide by 10 on both, right? So top and bottom, if I divide by 10, I get 29 pi over 18. 29 is prime, so I'm done. 38 is 29 pi over 18. We don't want to get the decimal values of this because that's messy. We want to leave it as such, okay? Because again, this is an exact measurement. Let's go to 39. All right. Negative 480 degrees. The negative has no bearing in terms of how we change things from conversion standpoint. Clearly this is a negative angle. It's going to go clockwise around the circle. But again, as long as you make sure that your radian measurement, because we're trying to go to radians, has a negative in it, we're good. It has no change whatsoever to how we multiply. So we're trying to get to radians, so I'm going to multiply by pi over 180. This is going to be negative 480 pi over 180. We can do this a couple times, right? So I know they both have a 10 in common. So let's do negative 48 pi over 18. I know I can divide by 6, right? So let's divide by 6. This is going to be negative 8 pi over 3. And I can't go any further. So negative 8 pi over 3 is my answer. And this is totally okay, everybody. If you're trying to just say, well, I know it's got a 10. I'm not exactly sure how to go other than that, but I know it's got a 10. You can do that. I just did. And I teach math. Okay, number 40. Number 40 already? I'll tell you what, time flies when you're having fun, huh? Time flies. Number 40. Where are we here? 10 pi over 9. Okay, radian measurement, try and get to degrees. So when he barks like that sometimes, I just laugh because it's hilarious. Radian measurement, I want to get to degrees, so I'm going to multiply by 180 over pi, because again, I'm trying to get rid of the pi measurements. Let's have them cancel. Cross cancellation makes this a lot easier. I could certainly multiply 10 by 180 and make a mess, but I know that 9 will go into 180 20 times. So let's just do 10 times 20, which is 200 degrees. Right. So number 40 is going to be 200 degrees. All right. Okay. Last 10. So we'll do 41, and we will stay. No, let's not stay in the same. So let's get out of this. Let's get out of this, huh? Let's move on to something harder. 41. Last 10. Okay. DMS conversions. DMS stands for degrees, minutes, and seconds. It is a quick reference for us to convert degree measurements in terms of degree decimals to degrees, minutes, and seconds. When I say degrees, minutes, and seconds, you might recall from a previous video, I'm looking for things that are more like longitude and latitude, basically to find out where you are on the map. Now, in terms of problems, what does that look like? Well, if I were to give you the longitude, latitude of 2 different cities, like let's just say 2 different cities in the United States, we could use DMS to find out the actual mileage, the difference in how far apart they are using this process. Now we're going to get there obviously, but for right now we just want to use the conversions. So here's what we need to do. Number 41 is 110 degrees, 52 minutes, and 11 seconds. Think about the unit circle, think about the circle on the coordinate plane and where we are falling on this coordinate plane. 110 degrees is a positive angle and it's a little more than 90, so it would open up as an obtuse angle. It's not 111 degrees and it's not 109 degrees. It's 110 degrees. The 52 minutes and 11 seconds, we'll think of it like this. If 60 minutes is 1 revolution, we're really close to another number or another degree measurement, right? So if this went to 60, this would have been up to 111, right? If this goes up, the seconds part, if that went up to 60, this would make it 53. Think of a clock, a stopwatch even, right? So all these things have something in common. We'll get there. So here's what we need to do to convert it to an actual degree measurement in terms of decimal value. The 110 stays, but the minutes, I need to find that ratio. And there are 60 minutes in an hour, or there are 60 minutes in another degree measurement in terms of our trigonometric circles. So I'm going to do 52 divided by 60 and get a decimal. If I have 60 as my ratio denominator of minutes, I need to have an equivalent ratio denominator of seconds. And there are 3,600 seconds in that same degree measurement of that minute or hour, right? We can think of that as the hour. So I'm going to do those 2 conversions, and I'm going to see what I get in my calculator. So 52 divided by 60 is going to be a pretty high decimal. That's going to give me 0.86 repeating. I just want to get those 2 decimal places. Typically what happens with the seconds is it bypasses the 2 zeros after the dot, and then I get 2 more values here. You'll see what I'm talking about in a second. 11 divided by 3,600 gives me 0.00305. Well, we'll just do 305, but I'm going to round that last decimal place up to 1. So my answer is 110.8631 degrees. Final answer. And again, this is really close to 111. If this was a little bit more and this was a little bit more, I probably would get to that 111. But I'm just using conversions to go from DMS, degrees, minutes, seconds, to decimal degrees. It's the same exact number in terms of what it represents. The value is the same. It's just a different way to represent it, okay? So when you see minutes and seconds, like the little ticks, you are going to do division by 60 and division by 3,600 to get here, right? So number 41 is going to be 110.8631 degrees. And we'll round it to 4 decimal places because that was a 0, but the next number was a 5. Let's do some more like that. Number 42. We'll cross out the ones that I'm done with. Okay, 241 degrees, 9 minutes, 12 seconds. All right, again, the 241 stays because that's a solid integer value of the degree measurement. 9 is a minute, I'm dividing it by 60. 12 is a second, I'm dividing it by its ratio, divided by 3,600. I'm going to do that in the calculator, and I'm going to get values that make sense here, right? So 9 divided by 60 is 0.15. It actually terminates, so that's really good. And then 12 divided by 3,600 gives me 0.003 repeating. The 0 would have been here and here, and I'm going to do 3, 3. The final answer is 241.1533 degrees. This is very strange, something that you probably haven't ever done before, right? And sorry, these are just degree measurements on the side. I'll make the next one over some more. Let's do one more like that, and then we'll do the reverse. Okay. Number 43, 304 degrees, 58 minutes, 47 seconds. Okay? Again, this is really close to 60, which means that our decimal degree measurement is going to be almost 305, right? So let's do this. 304. Point. Divided by 60, divided by 3600. Let's see our values. 58 divided by 60 is going to give me 0.96 repeating. Let's just put the 0.96 for now. And then the 47 over 3600 is 0.013. Okay, so here's what we want to do with this. I'm going to make this go up to a 7 because that was a 6. But because there's a 1 here, there is actually an overlap. And then that's a 1 and a 3. Now, I'm going to need the 4th decimal place, which is going to be a 0. Because there was an overlap with the 7 and the 1, meaning when I divided 47 divided by 3600, I actually got 0.0130. That's not typical. But because 47 is higher up on the scale of 60 or 3600, I'm going to have another value here that I don't want. I'm actually going to be adding down, right? So this is going to be 304.9830 degrees. Done. Through practice, you're going to see that more often. It just hasn't happened yet, obviously. So we've got 304.9830 degrees. Now let's do 2 problems that are the reverse. Instead of giving you DMS format, I'm going to give you decimal degree format, and we'll try to reverse the process. So 44 is, let's do 80.26 degrees. Okay, here's how this works. Our whole number value comes down. That stays no matter what. That 0.26, if you remember from the last problems we did, that's the overlap of the minutes slash seconds combination. That 80 is going to stay valid for the whole time for us. That's the degree measurement, the whole number degree measurement. Now, if we divide it by 60 and then eventually divide it by 3600 for the first 2 decimal places, tenths and hundredths, and then thousandths and 10,000ths, I'm going to have to multiply by 60 a bunch of times to get back to that value. First, we take the point, the decimal place, and we multiply that by 60. Now that's going to give us 15.6. The whole number value of that answer is the minutes. Next, we take the decimal remainder part, and we multiply that by 60, which is going to give us, obviously, our seconds. Shush, buddy. And that's going to give me 36 exactly. Final answer. So what did we do here? We take the decimal only part, multiply by 60. Whatever that answer is, the whole number value is the minutes. The decimal part of that we take out and multiply again by 60 to get the seconds part. All right? So our answer for number 44 is going to be 80 degrees, 15 minutes, and 36 seconds. Okay? Let's think of it like this for a second. If I said it was 80.26 degrees on an angle, well, 0.26 degrees is like a quarter of another degree, right? Think if this was dollars. Think if this was money. $80.26. Well, 26 cents is a quarter of a dollar because 25 cents is a quarter. In terms of minutes, 15 is a fourth or a quarter of 60. Cool. 45. Hopefully that made some sense. It's okay if it didn't. 45. Let's go 222.44 degrees. Again, I have this in decimal degree measurement. I want to convert to DMS. So the whole number value of 222 sticks. That's my degree measurement. The 0.44, I'm multiplying by 60. And I am taking 0.44. I'm not doing 44 because that would be a mess. 0.44 times 60, that gives me 26.4. The 26 is my minutes. The 0.4 multiplies by 60. And that's going to be 24. Final answer. 222 degrees, 26 minutes, and 24 seconds. All right, 5 more problems. Woof. We're getting there. All right, part 5, our last part. Circular motion. This is some difficult stuff. Let's take it one at a time. Number 46. Before we get into 46, let's recall the arc length measurement formula. Now again, we're not doing the old school formula. We're doing the new school one because that's more cool. So the new school formula is S, which stands for arc length, is going to equal to R, which is the radius of the circle, times theta, which is the angular measurement or angle of that circle that it opens up to. So we have a couple of things here. This is our new formula. I don't know why I wrote the A like that. I'm sorry. Number 46, take a look. I've got a circle here. And that circle looks a lot more pronounced than it actually is on the screen, so I apologize. So we have a central angle, one that opens up from the center of the circle, and it's 100 degrees. The radius is 7, and I'm trying to find arc length. Okay, so let's go ahead and do this. So if I have my arc length, I'm going to be multiplying the radius times the measurement of that circle. Now, the problem is that this is in degrees. I need that to be in radians, because when we talk about the new arc length formula, the stipulation is that we are in radian measurement for theta, not degrees. So the first thing we need to do is we need to convert. So we're going to convert this 100 degree measurement to radians. And to do that, we're going to do pi over 180. And that's going to give us 100 pi over 180. Let's simplify that to make that a little bit nicer looking. I know I can divide by 20, top and bottom. So that's going to give me 5 pi over 9. Okay. Now that is the radian measurement of that angle. Now let's multiply that times the radius, because this is theta. So back to our formula, we have S equals R, which is 7, times theta, which is 5 pi over. And we have arc length is going to now equal 7, which is the radius, times 5 pi over 9. That's going to give us S equals 35 over pi. I'm sorry, 35 pi over 9. Now, I need the degree measurement, but I need the decimal of this. So the decimal is going to be what we're looking for here. So I'm going to actually just make this a decimal. So let's do 35 times pi divided by 9. In your calculator, though, be really careful. Don't hit 35 pi divided by 9, because your calculator is going to do 35 times whatever pi divided by 9 is. So we'll do 35 times pi first. Hit enter. Then divide that by 9. And we're getting our final answer. The arc length is going to be 12.22. We'll round to the hundredths place. So that's my value. That's my final answer. So again, what did we do here? Step 1, convert to radians. Step 2, multiply by the radius. And then step 3, get the decimal value of this radian measurement. Bam. So number 46 is 12.22. Ooh, it's not degrees. It's, what was it? What was it called? Units. I don't know exactly what it was, but it was units. All right, moving on. All right, number 47. Same type of problem. I'm looking for arc length. That's a nice circle. So we've got a central angle, and that's 140 degrees. The radius is 5. We want to find, actually this is a good one. We want to find S. We want to find the major arc. We don't want to find the minor one. So that's going to change things a little bit. I am not actually going to use 140, because if I used 140, then I'd be looking for the minor arc. I want to find S, which is this major arc. So we just need to do a little finagling. If I know a circle is 360 degrees and this portion is 140, what's the other portion, right? So 360 minus 140 is 220. 220 is what I'm going to be using for my radian measurement once I convert. Step 1, convert to radians. 220 pi over 180. I can divide by 20. So if I divide by 20 on both of them, that's 11 pi over 9. Okay. Now that is my theta measurement. So I need to multiply that by the radius of 5 now, right? So I'm going to get 55 pi over 9. Final step, give me the decimal value of this measurement. (55 times pi, enter, divide by 9. And we're going to get 19.20 units, which is the measurement of that arc. All right, let's move on. All right, this one's gonna be a little more challenging, 48. An arc length of 100 meters. Sub-tens. Hey, Titan, did you write this? You know how I feel about that word sub-tens. A central angle with a radius of 50. Okay, an arc length of 100. Doesn't really matter where it is. Okay. Radius of 50, find the measure of theta. All right, so we have to do some crazy stuff here. This is the arc length. It's 100, so we'll label that as S. 50 meters is the radius. So I have S and R here, I need theta. All right, so let's just go ahead and make it happen. 100 is gonna equal 50 times theta. Divide by 50 on both sides, and I'm gonna get 2. And 2 is gonna be theta. Okay, so what do we have here? This is a radian measurement. We have 2 radians, which is theta. Now, it said I wanted the degree value because I want the degree measurement of theta. I don't want radian measurement. So let's think about this for a second. If I have 2 radians, how many degrees is 2 radians? Well, how many degrees is 1 radian? Well, if we talk about the measurement value of what 1 radian actually is, 1 radian is about 57.8 or 6 or something like that, because that is almost a third of 1/2 of a revolution, or the 180 we're looking for. So we're going to multiply. We're going to do the 57.3 or 6 or whatever times 2. And that's going to give us a value of 114.6 degrees. Now, where did I get that from? We got something crazy here, and we got 2 radian answers. 2 radians, well, 1 radian is, again, it's a little bit less than 60 degrees, about 57.236, something like that. I forget exactly. We just multiply that value by 2, and that's going to give us 114.6 degrees. And that makes sense because we have an obtuse angle here. So 48 is going to be about 114.6 degrees. If you give me 115 degrees, that's also totally fine, okay? More to come on problems like this. 49, we're almost there. Find the length of an arc that's sub-tens, a central angle of 45 degrees, and a circle of radius 10, all right? So we got a radius of 10, and we got a central angle of 45 degrees. All right, first step, I'm gonna take that 45 degrees and translate it over to, or convert it over to radians. So 45 degrees times pi over 180 is gonna give me 45 pi over 180, and that's 1/4. So this is gonna be pi over 4 is my theta measurement. So then I'm gonna multiply that by 10. So 10 times pi over 4 is gonna give me 10 pi over 4, which simplifies to 5 pi over 2. And again, I want the decimal value of that. So in our calculator, we're gonna do 5 times pi, enter, and divide by 2, which is gonna give us 7.85 units. All right. We are on our last one. I'm super excited. I'm super excited. 7.85 units. All right. Whew. Talk about a marathon. I used to run them. Really. Really. Not in a while. All right. Find the radius of a circle. Oh boy. If an arc of length 6 meters on the circle subtends a central angle of pi over 6 radians. Okay. Arc length is 6, so that's S. Central angle of pi over 6 radians. All right, so we got a couple things here that are real nice. We know that we have our theta measurement, our central angle measurement of pi over 6, so I don't have to do any conversions there. We know that 6 is going to represent the S measurement, so we're going to have 6 equals pi over 6 times R. All right, well, let's go ahead and divide by pi over 6 on both sides. Now again, dividing by a fraction, I'm really multiplying by the reciprocal, right? So this is going to be 6 over pi on both sides. This cancels, which leaves us with R equals 36 over pi. Okay, let's just get the decimal value of that. We'll call it a day for the radius. 36 divided by pi, make sure you do your division sign, and I'm going to get R equals 11.45. We could also say, 46, sorry, if I'm rounding to the hundreds, sorry. 11.46. I could also say the radius is 36 over pi, but I'd really rather not because I want the decimal value so I can actually kind of see, because the arc length was in an actual measurement that I could value. All right. Thanks so much for tuning in to this episode of the Titan class. Have a fantastic day.